Okay, for page 4 of the addendum for applications of differential calculus. For a given mass of gas in a piston, P times V to the 1.5 equals 400, where P is the pressure in Newton per meter squared, and V is the volume in meter cubed. Suppose the pressure increases at a constant rate of 3 newtons per meter squared per minute. Find the rate at which the volume is changing at the instant where the pressure is 50 newtons per meter squared. Okay, so, maybe some of these like mechanical problems with like pistons and diagrams and things might scare you, but actually like a lot of times these problems, they already give you the formula. So really it's easier than one of the problems that like volume of a water container or things that they know you can figure it out. These sometimes might be easier because they actually give you the equation. So we have the equation already. Now they just ask us, okay, what if we change the pressure at this rate, okay? Now tell me how the volume changes when that happens, okay? Because when the pressure changes, the volume has to change because, look, they're multiplied together and they always give the same number. So if one changes, the other has to change also. So we know that we need an expression with dp dt and dv dt in it because one of them they gave us and the other one we want to know. If we need derivatives in the expression, what better way to get derivatives in an expression than taking the implicit differentiation, right? That is a product. P times v to the 1.5 is a product of two different variables. So we do need to use product rule, which would be, so we'd get P times the derivative of v to the 1.5, which would be 1.5 v to the negative, v to the 0.5. Okay, we reduce the exponent by 1. And then we need to add that to derivative of, oh, I'm sorry, I forgot something. And then chain rule of v, so it would be dv dt. Then we need to add that to dp dt, and then we leave v 1.5 as is. So we did the product rule on the left side, and the right side, the derivative of 400 is 0 because it's constant. Okay, now they tell us that the pressure increases at a constant rate of 3. So dp dt, which is the rate at which the pressure changes, is positive 3 because it increases at a rate of 3. Find the rate, okay, and then now let's try to figure out some of the other things. We are trying to figure out how the volume is changing. So dv dt we're not going to know until the very end. So we basically want to know P and V now. Well, it says find the rate at which the volume is changing at the instant when the pressure is 50. So we know P is 50. Okay? And anything else we need? Volume. So how do we figure out what the volume is? So the volume is known from the pressure by this equation here. So PV to the PV to the 1.5 equals 400. We know that P is 50. We know that the volume is, we don't know. So V 1.5 is equal to 400 divided by 50, which is 8. V to the 3/2 equals 8. Let's take the cube root of both sides. So we'd have V to the 1/2 equals 2. Then let's square both sides. V equals 4. So the volume equals 4 at that instant. So we can also put 4 in for V here and 4 in for V here. And so now we have pretty much everything we need to know. So basically the equation is going to be 50 times 1.5 times 4 to the 0.5. 4 to the 0.5 is 4 square root of 4, which is 2, dv dt, plus dp dt is 3. Then 4 to the 1.5 is the 4 to the 3/2, which is the square root of 4 cubed. So the square root of 4 is 2. 2 cubed is 8. So now we got 100 times 1.5, which is 150 V dash, plus 24 equals 0. V dash, oops, and then we subtract 24 to the other side, so we have 150 V dash equals negative 24. V dash equals negative 24 divided by 150, which is equal to negative -0.16. So the volume is decreasing by -0.16 meters cubed per minute. Okay. Number 13. You have a triangle, PQR. It's right angled at Q, and PQ is 6 long. QR increases in length at 2 centimeters per minute, blah, blah, blah. Remember, the first thing you want to do is you want to draw a diagram in the case that they don't give you the diagram in the equation already. In this case, we do need to figure out an equation, so definitely draw a picture. Good advice in general for math and physics. So we're going to draw a PQR triangle. P, and the Q is the right angle, so it looks kind of like that. PQ is 6 long. QR increases at length by 2 per minute. So this is the derivative of QR, okay? I'll just put in a circle so that we don't confuse it with the length. Find the rate of change in the angle QPR at the instant when QR is 8. When QR is 8. Okay, so let's call QPR theta, and let's call QR y. Okay, so basically what they're saying is the derivative of y equals 2, and they want to know d theta dt, or theta dash, when QR is 8 long, when y is 8 long. Okay, so basically they want to know theta dash when, okay, y equals 8. And the other two pieces of information are like constants. So y dash always equals 2, and x, which we'll call this x, is always 6. Okay? And since it's a right triangle problem, then we're either going to use SOHCAHTOA, or we're going to use Pythagorean's theorem. Pythagorean's theorem doesn't have angles in it, so we want to use like SOHCAHTOA. Which do we want, SOHCA or TOA? In this case, we got opposite and adjacent, so we want to use TOA. So let's write out the expression for tangent, which would be tangent theta equals y divided by x. And don't substitute anything in yet, because we need to figure out what's constant and what's a variable, right? So in this case, let's look now. The constants were y dash equals 2 and x equals 6. So we can't safely put 6 in for x, okay? So we do know that, and theta and y are variables. So it's this relationship here. And now we need to take the derivative with respect to t in order to have a relationship between y dash and theta dash, which we want to figure out. So let's do that. By the way, be careful, because whenever you take, we're going to do the implicit differentiation now to introduce d theta dt and dy dt into our equation. Remember that whenever you are taking derivatives of a theta, you use the formulas from the formula booklet, you are assuming that theta is in radians. Okay, so this would be secant squared theta d theta dt, and the right side would be dy dt times 1/6. And now maybe we can substitute stuff in. We already used x equals 6. Y dash equals 2. That would go here. We need to figure out what is theta at the instant when y equals 8. Let's see. So that would be, we would use this equation here. So tangent of theta equals 8 divided by 6 equals 4/3. So what would be the inverse tangent of 4/3? So I'm going to do inverse tangent on my calculator. Make sure you're in radians mode, and it gives you that the theta value would be 0.927 radians, which is pretty close to 60 degrees. You can see that I drew this triangle wrong. That should be taller than it is wide. And now I can put 0.927 in for theta, but they want secant of theta. So let's see, secant of theta, remember, is 1 over cosine. So we could do cosine of 0.927, which would be 0.6. That makes sense, right? Because it would be 3 over 5. Okay, this is a 3, 4, 5 triangle. So secant will be 1 over 0.6, and secant squared would be 1 over 0.6 squared. So this would be 1 over 0.6, which is 1 over cosine squared. And then, as everything else known, yeah. So now we got, on the left side, we got 1 over 0.6 squared, and I'm going to multiply both sides by 0.6 squared so that we can put it on the right side by itself. So we'll have theta dash equals 0.6 squared times 2 divided by 6. And that is equal to, let's see, 0.6 times 2 would be 1.2 times 0.1, which would be 0.12 radians per is it second? Per minute. Okay, because this is per minute, so this would also be per minute. So 0.12 radians per minute. Okay, last one. A farmer has a water trough of length 8, which has a semicircular cross-section of diameter of 1 meter. Water is pumped into the trough at a constant rate of 0.1 meter cubed per minute. Okay, show that the volume of water in the trough is given by V equals theta minus sine theta, where theta is the angle illustrated. Okay, show that the volume of the water is given by that. Okay. All right, so the first part is not even calculus, it's just trig or whatever. Let's figure out the volume of the water. Remember that what they're drawing is a cross-section, which means that really it's a tank, which looks kind of like this, and the length of the tank is 8 meters. Okay, the length of the tank is 8 meters, and the width of the tank is 1 meter. So when we figure out the volume of the trough, we want to figure it out as a function of this theta value. Okay, so do you remember in unit circle we figured out like these ice cream cone shapes? Basically what we do is we figure out the sector, which is this whole thing, and then we subtract out the triangle. So the two equations you're going to use for this are the pizza slice formula, which is 1/2 theta r squared, where theta is in radians. That's the pizza slice. And then you subtract out the triangle, which is 1/2 r squared sine theta. Remember that? 1/2 AB sine theta. Okay, so that gives you the ice cream part of the ice cream cone. And so that is our formula to figure out the cross section. Now, of course, to get the volume, we would need to multiply that times 8, right? Because we would make it 8 long to get the volume. So let's try to simplify that. So the volume is equal to 8 times 1/2 blah, 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 minus 1/2. Let's distribute the 8. So then we'll have 4 theta r squared, theta's in radians, of course, minus 4 r squared sine theta. Let's see, what's the radius? Oh, the radius is 0.5 because the diameter is 1, right? So it's 4 times theta squared, 0.5 squared, minus 4 times 0.5 squared sine theta. Oh, wait a second. 0.5 squared is 0.25. 4 times 0.25 is 4 times 1/4, which is 1. So we basically get theta squared minus, and this also multiplies together to become 1. We get theta squared minus sine theta. Oh, no, it's not theta squared. Look. What am I doing? It is theta minus sine theta equals the volume. Okay, so that's what we wanted. So now we have an equation we can take the derivative of to introduce dv dt and d theta dt which we kind of want as part of our relationship here. So we take the derivative of the left side. Derivative of v is dv dt. The derivative of theta is d theta dt. The derivative of negative sine theta is negative cosine theta d theta dt because of the chain rule. Okay? So now we have this expression, and we know a lot of the pieces that go into here. The hint says first find d theta dt and then find dh dt at the given instant. Okay, so we haven't even talked about h yet, but h would be like the height of the water here. Okay, and then let's say that the y is this part of the triangle. So let's see what we got here. We'll like plug in some of these values and see if we're missing anything. We want to know d theta dt. So first we'll put in dv dt. dv dt is plus 0.1 because that's the amount of water that's being put in per minute. So I'll put plus 0.1 there. d theta dt is what we want to know. Let's factor out d theta dt. So we'll have 1 minus cosine theta. And cosine theta we should be able to figure out using trig, right? So let's see. The cosine of theta, let's see, can we figure out what theta is at this time? So let's draw half the triangle. This angle here is half of theta. We're at 0.5 here. We know for this instant that we're looking for that the water is 0.25 deep. So that means h is 0.25. If h is 0.25, what is y? Well, we know that the radius is 0.5, so since h is 0.25, then y must also be 0.25 meters. Okay, so this is 0.25. This part here we don't know, but maybe we don't need to know. So if the hypotenuse is 0.5 and the y value is 0.25, that is a 1 to 2 ratio. What kind of triangle has a 1 to 2 ratio between the adjacent and the hypotenuse? 60-degree triangle, right? So we know that angle is 60 degrees. So the theta at this particular time, when the water is 0.25 meters deep, is 120 degrees. Because if you look at the theta value is like double 60 degrees. So then we could say, okay, so here we want the cosine of theta. The cosine of theta is the cosine of 120 degrees. The cosine of 120 degrees is negative 1/2. Okay, so we got 0.1 equals theta dash 1 minus 1/2. So 1 plus 1/2. So theta dash is equal to 0.1 divided by 1.5, which is it would be 1 over 50. Okay, so theta dash is 1 over 50. So now we know d theta dt, which they advise us to do first. Now they say find dh dt. Okay, so dh dt, let's see. Let's figure out the relationship between h and y. H and y, as we said, if we add them together, we should get 0.5. If we, and then we also know that the relationship between y and theta, because we know that the cosine of half of theta is equal to y divided by 0.5. So let's try to let's see. We'll put 2y here because y divided by 0.5 is 2y, right? Cosine theta divided by 2. Let's get an expression that relates h with theta. So let's take y equals 0.5 minus h, and we're going to put this here. And then so now we'll have cosine theta divided by 2 equals 2 times y, which will be 1 minus 2h. Okay? And then let's take the implicit derivative of this expression and then try to make a differential equation with d theta dt and dh dt in it, and then we can use this to figure out what dh dt is, shall we? So the derivative of the left side would be negative sine theta divided by 2, and then do the chain rule. We'll do multiply that times 1/2, and then equals derivative of 1 is 0, derivative of negative 2h is negative 2 dh dt. Oh, oops, I forgot something. So the chain rule of theta divided by 2 would be 1/2 times theta dash, right? Theta dash is 1 over 15. We can substitute that in. We know that theta divided by 2 is 60 degrees. We can substitute that in. Sine of 60 degrees is square root of 3 over 2. So negative square root of 3 over 2 times 1/15 over 20, which would be, or 1/15 divided by 2, which would be 1 over 30, equals negative 2h dash. The negatives cancel out. Divide both sides by 2, so we'll end up with square root of 3 divided by 120 equals h dash. And the units would be meters per minute. Meters per minute. Okay, and I think that's it. We're done with the addendum.